right, happy Thursday, everyone. We're going to continue with our problem set. Again, if it works out to make a copy of this stuff for distance learners, go for it. But I'm not requiring anyone to copy. It just sort of means you got to kind of go back and forth a little bit, read the problem, do it, so I always like to have a hard copy. It kind of makes a quicker reference. All right, so what we're going to do here today is talk about the third and final quantity that we're going to be dealing with gases, and that would be temperature. So we've got pressure, volume, that's Boyle's law. Now we're going to throw temperature into the mix. Now, we're going to define temperature as the average kinetic energy of all the molecules. Okay? I'm going to give you a little example here that will help you kind of understand what we mean and how energy and temperature are related. And we're going to use the best basketball player of all time, Michael Jordan. Not up for debate. Much better than LeBron James. You could try to convince me otherwise, but Michael Jordan, I think, is the greatest of all time, the GOAT. So we're going to do a little thing with him, but before that, need to say who the best woman basketball player of all time? Of course, our very own Maya Moore. As you can see, she plays for the Mayo Clinic Verizon Nike team, but there is a small indication of a logo of the Lynx right there. But the reason I think that she is the best, and I think you find some people that would agree with me, is that every place she ever went, they just won championships. Just a force. And she retired right in the prime of her career, which it takes some guts. And she's done some pretty heroic causes for justice since then. So she's my hero. But we're going to use Michael Jordan because he has just had some Gatorade. That's the Gatorade symbol right there, which we know from our electrochemistry unit has electrolytes in it. But apparently, there was a commercial series years ago that if you drank Gatorade, you would sweat out whatever color Gatorade you drank. So obviously, Michael's had some orange Gatorade right here. So what I want to do to help you understand temperature, we perspire to cool ourselves off. So how does that happen? Well, let's zoom in on that little drop of sweat on Michael's forehead right there, okay? See that amazing graphic right there? That circle becomes that circle. So here is the drop of Gatorade sweat. Now, all of the molecules, whether it be gas, liquid, just the nature of them is that they have different amounts of energy. And these arrows represent the energy of those gas molecules. Okay? So this one has the most energy, medium amount of energy, and low energy. Well, that will correspond to temperature. So right now, the average is kind of right in at about this medium. But what's going to happen is the one with the most energy will break free and become a gas molecule, leaving behind it two with lower energy, therefore lower temperature. So the higher energy molecules break free, thus lowering the average kinetic energy and creating a cooling effect. So this is cooler just by the nature of it. So that drop of sweat comes to the surface. This is something that we evolved millions of years ago, the ability to cool our bodies. It's very important our bodies stay at the same temperature. So as you're exerting yourself, it keeps heating up, and if you get those beads of sweat, they'll pull off the highest energy, and you really feel this when you get out of the swimming pool on kind of a medium cool day and that wind blows, you can really feel that energy being pulled off of your body. So and then eventually then that medium-sized one will break free because it'll be near the surface, and then the cooling even gets more. And the average kinetic energy of those molecules is lower, and that's where that comes in. The average kinetic energy is temperature. So when we talk about, we just set a record high the other day, a couple days ago, and that record high simply meant that the gas molecules in the atmosphere had more energy than they did ever before on that day in history. Okay? So, kinetic energy, there is an equation that you probably learned in probably 9th grade, I would guess. Kinetic energy equals 1/2 the mass times the velocity squared. Okay? Ke equals 1/2 mv squared. So velocity is super important. We talked about this in class a couple days ago, that how important speed is in terms of defining and giving energy to those gas molecules. And so the smaller ones are moving faster, and the bigger ones are moving slower, and that's why 1 mole will equal 22.4 liter, whether it's little, medium, or big, because the average kinetic energy can be defined by both movement and size of the molecule. So mass velocity squared, that's temperature. And I think it's important to have a real good understanding of what temperature is. Now, we measure temperature in Celsius. We're going to kind of stay away from the Fahrenheit, maybe a bonus or something question, but we're in the metric world, so we're going to stay with degrees Celsius. There is a scale called the Kelvin scale that is Celsius plus 273. Well, it was found out that the absolute lowest temperature you could ever get, and we could actually even do experiments to kind of extrapolate that and say the lowest temperature you could ever get to is about 273 below in Celsius. So this guy by the name of Kelvin said, hey, let's come up with a new scale so that we never have to worry about temperature being 0, because then that'll screw up all these formulas that we're going to do. And we never have to worry about the temperature being negative, because then we get silly things like negative pressure and negative volume, which really are not going to make sense in a lot of these contexts. So the Kelvin scale, and notice there is no degree symbol on the Kelvin, is designed so it's never negative. So therefore, take the absolute lowest, which would be 273, and then add that to the Celsius temperature. Okay? And we will always, always, always use Kelvin in these gas law problems when we're setting them up, like the Charles law and the combined gas law that we're doing today. If you forget to add 273 to your Celsius temperature, you're going to get the incorrect answer, because the whole system is set up on the Kelvin scale. Okay? So, we had talked about STP. You know what standard pressure is. Now, standard temperature is 273 Kelvin. That sounds nice and warm. But that's 0 degrees Celsius. That's the freezing temperature of water would equal 273 Kelvin. All right? So those concepts are all going to be very, very important in terms of understanding temperature. All right, so we had Boyle's law, we had Dalton's law, and now we're going to have Charles' law. It was actually, the guy's last name was Charles, so that's why the apostrophe is right there. So his name is not Charlie or anything like that. So this is Charles' law, and this guy figured out the relationship between this. And if you think about this now, if you're going to heat something up, now take a balloon and you heat it up, the balloon is going to expand. It's going to get larger in size. That's called, boom, boom, a direct relationship. So we're not going to be able to stack the letters next to each other like we did in Boyle's law. So Charles' law, if you have volume going up, temperature is going to go down and vice versa. Okay? So the way we show that mathematically is this. It would be initial V1 over T1 equals final V2 over T2. All right? So that is the Charles law equation. I'll show you that cool graphic of flying that in there again. Nice, huh? I worked hard on that. All right, so that's Charles' law, and there's some stuff jumping around back there that I'm going to talk about in a little bit. But then there's also the combined gas law. I want you to think about this. So if we have pressure, volume, and then temperature on the bottom, you could do all of this combination like this. Okay, so all we've done, you can see Boyle's law in there, and you can see Charles' law in there, and you just combined them. And it's called the combined gas law. Okay? Now, there is another, so we're going to, I think I'm missing something. I need to check something out here. All right, sorry about that. I thought we were missing a problem, but this is the first Charles law problem, 11a. It says that if a gas has a volume of 10 cubic meters at standard temperature, what would the volume occupy if the temperature was doubled? So to do a problem like that, we will do the same strategy we did when we did a Boyle's law problem. You start with equation, so there's your formula, and then you do setup, because it gave us 10.0 meters cubed, and then the temperature was at standard temperature, so you're going to have to know that. When you do these problems, I won't always say 273 Kelvin, but at its standard temperature. And then they said, what would happen if the temperature was doubled? And that's exactly what we're doing here. So if this is a direct relationship, so you know probably what's going to happen if you double up and up. Double one, you're going to double the other. So just to confirm the math on that, a good way of doing this is just to cross multiply and then solve. Okay, so I'm just going to do that on the calculator here and take 10 times 546 and then divide that by 273. You cross multiply and solve for x, and your stupid calculator says the answer is 20. Well, that only has one sig fig, but that is the numerical answer, so you're going to say 20.0, just like that guy was 10.0, 20.0 meters cubed. So that's 11a. In the next video, we're going to continue on and talk about how we're going to attack the rest of these problems.